Good day to all of you. Today, we shall discuss on one more important aspect of DC-DC converter, which is the magnetic components. Recall in the last class that we mentioned that to design a DC-DC converter, three main components and the selections are important. One being the power semiconductor switch, the other one is the capacitor, and the third is the magnetic component, both the inductor and the transformer in case of isolated DC-DC converters. So, today the objective is that we try to understand something about the magnetics, how we would go about designing this inductors and transformers, such that it can be included in a practical DC-DC converter. So, the magnetics have always been a domain which has been pretty much difficult to understand and implement. However, once a design is performed with the magnetic components being passive, they are very robust. So, nothing happens to them, unlike the power semiconductor switches or the capacitors, both of which may blow once the rating is exceeded, and the magnetic components, the only rating that can be exceeded is the currents and the saturation levels, which will cause other components to get damaged, not itself. So, let us see the magnetic components from two viewpoints. One viewpoint is the electrical, and the other is the magnetic domain. So, now these two are tightly interfaced and they interact through a window through which there is energy transaction. So, let us say we call this as the energy port or the power port. So, this is the port. It is like all ports, electrical ports. It has two conductor points, two wires, and two variables. So, on the electrical side, we have V, the voltage, and I, the current variables. Now, V is the potential across the port and I is the current through the leads of the port wires. And now, on the other side, you have a potential variable and a flow variable. The potential variable is called MMF, the magnetomotive force, and the flow variable is called d phi by dt. Now, these two domains are linked together by two very powerful and fundamental laws, the Faraday's equation. You also have the Ampere's rule or equation. Now, these two important rules, principles, govern the entire interaction between the electric domain parameters and the magnetic domain parameters. So, let us say we have the potential variable V, voltage across the port, and I is the current through the port on one side. You have the MMF, magnetic motive force, the potential variable on the magnetic domain, and rate of change of flux, not flux, remember rate of change of flux. In fact, the MMF is flux by reluctance. MMF is flux into reluctance, and the flow is the rate of change of flux. So, now how are these variables related? The relationship, the linking is between the cross variables. The potential variable on the electrical side is linked to the flow or the kinetic variable on the magnetic side. The kinetic variable on the electric side is linked with the potential variable on the magnetic side, and both these linkings happen with the parameter n. And what is this n? N is nothing but number of turns of the winding. So, to make sense out of what we have discussed till now, let us see how a practical magnetic component looks like, and try to understand what it is. Now, here I have a piece of magnetic component. Observe this is the core, this is a material, ferrite material, and here in between you see the bobbin, and on the bobbin you see the windings. These are enameled copper windings. Okay. You can remove the core. The core is now split into two halves. The bobbin along with the copper winding can be removed. The copper winding is having two terminals here. Now, you have two halves of the core. Now, this is the copper current carrying copper conductor which has n turns, and these n turns is wound around the magnetic core material. Okay. So, let us get back to this later on, but for now assume that we are able to wind the copper coils as shown, and that is the number of turns n that I have been talking about. So, now coming back to the whiteboard. So, the n is the number of turns, copper turns, which is wound on the core, magnetic core. And how are these related? So, V is equal to N times d phi by dt. This is called Faraday's law. The voltage across the winding is equal to N times the rate of change of flux within the core. So, that is the first. Now, to link the MMF and the current, we have the Ampere's rule, which states N I, which is the ampere turns, is equal to MMF. So, this will come as a result of the Ampere's rule. So, the Ampere's law, by Ampere's law we have I, which is integral of H dot dl, where L is the magnetic length. Integrating over the whole length, you would have I, which is H dot Lm. Now, if there are many turns, the force within the core is a cumulative effect of all the turns, and therefore, the N comes in to the picture. So, it is Ni, the cumulative effect of all the turns, which is integral H dot dl, and therefore, Ni, which is equal to H Lm, and the force field within the magnetic field within the magnetic core is given by Ni by Lm. So, this is as per the Ampere's rule, and from the Ampere's rule we have this, and from Faraday's law we have these. Now, these two laws are the most critical principles on which the entire magnetic field and the electrical domain interaction rests. So, now V is equal to N d phi by dt, MMF is equal to Ni. These two rules are the foundations for which all the other magnetic based equations that are used in design. Now, take for example, the power. power is V into I. And in the magnetic domain, what is it? In the electrical domain, you have a potential variable multiplied by a kinetic variable, which is power watts. Now, let us take the Faraday's equation, substitute it for the potential variable V. So, you have N d phi by dt into I is the power in watts. Now, from the second equation, MMF is equal to Ni. Let us combine these two and you will get d phi by dt into MMF is again power in watts. So, you see that the power in watts in the magnetic domain is also composed of the two variables, the potential variable MMF and the kinetic variable or the flow variable d phi by dt, product of which is watts power. Now, in the literature, you would see a very important graph B versus H. B is called the flux density, which is flux through the core by the core cross section area, and H we saw coming from the Ampere's rule N I by L N. Now, this would normally be a straight line like that, but it is not straight throughout. After some stage, the flux saturates and there can be no d phi by dt. Not only does it saturate, the core, magnetic core has memory. It demonstrates a clear-cut hysteresis curve in this manner. However, to understand, we shall consider the virgin specimen without the hysteresis, so that you get a clear understanding of what is happening within the core. So, let us take out the hysteresis portion. Now, this slope B by H is called mu, the permeability. Now, B, which is equal to mu H, B is nothing but flux by the area of cross section of the core, mu N I by L M. So, flux, which is equal to N I by L M by mu A. this is nothing but Ni by reluctance or MMF by reluctance. This is one very important relationship, flux which is equal to MMF by reluctance, and in the literature many a times it is called the Ohm's law of the magnetic circuit. However, remember that in the Ohm's law, this R is not the R, the dissipative resistance. It is more related to Q is equal to so this is more related to Q is equal to CV formula rather than I is equal to V by R. Now, this is the electrical equivalent. You can put it in that form, 1 by reluctance into MMF. Now, what is 1 by reluctance? I am going to introduce one more term called permeance, which is 1 by reluctance. So, permeance is more closer to your equivalent capacitance concept. So, phi which is equal to permeance into MMF. Now, compare these two. Flux is like the charge, MMF the potential, permeance is like the capacitance. So, the reluctance is 1 by capacitance, 1 by C equivalently. So, now let us go further. So, flux is permeance into MMF, which is Ni. So, N d phi by dt, that is I am multiplying both sides by N square di by dt and differentiating with respect to time. So, what do you see? You see that this from Faraday's law is voltage V, and this is equal to something di by dt, which is equal to inductance L di by dt. So, we define permeance into N square as the inductance value. So, inductance L is permeance into N square. This is an important relationship because in many of the core catalogs, this permeance value is given as what is called as AL factor. This is as a units of nano Henry per turn square. So, this is given in the data sheets in many of the gapped cores or the inductor type cores. this permeance is used to design the number of turns. Now, L value is obtained from your DC-DC converter electrical design based on the amount of current ripple that you want to have, the voltage across the inductor and all those things. This L value is obtained from electrical design. Then N, the number of turns that you need to put for the particular core would be L by lambda permeance square root, because this is nanohenry per turn square and root of it would give you the number of turns that you need to wind to get that value of L. So, this is a very important relationship. We can go one step further. L is equal to permeance into N square, which can be written as 1 by reluctance into N square. 1 by reluctance is mu AC by L m, mean magnetic length, into N square. Mu is nothing but mu naught, and relative permeability, core cross section area, N square by the magnetic length. This is another useful relationship in case you are unable to find the value of permeance from the core catalog, or in case you are using a transformer core for which you do not know the permeance. You are using a transformer core to build an inductance in which you need to insert an air gap. Under such cases, this relationship is useful, basically derived from the same relationship, only that you know the play of the variables within, the play of core cross section area, the mean magnetic length of the core which is given, relative permeability for the core material which is known, and this is the permeability for free space, which is 4 pi into 10 to the power of minus 7 Henry per meter. So, this way also the inductance L can be found out, but as the inductance L is obtained from the electrical side, L is known, core cross section is known from the data sheets of the core material, mu r permeability, relative permeability is known from the core materials data, mean magnetic length is known, and from that you can find out N. So, let us see how we now go about finding the inductor to the physical parameters in a logical way. So, on the mechanical side, we have what is known as core cross section area, you have the window area, you have B sat, again coming from the material, and on the electrical side we know how to get the value of the inductance, we know what is the current flowing through the inductance, we know what is the voltage across the inductance. And from here we know what is the energy in joules which the inductor will have to store. Now, from the electrical parameters, we need to arrive at the physical parameters such that you can select a physical core for winding the material. Apart from this, we also need to know what is the number of turns, what is the gauge of the copper wire, that is the thickness of the wire or the diameter of the wire which you need to wind. Now, these physical parameters we have to relate to the electrical parameter. So, first let us say from the electrical side we have the energy which can be easily found out. So, the energy E is half L I m square. This is the maximum energy that the inductor will have to store. Now, what is this I m? Typically, in an inductor DC-DC converter, if you plot the inductor current, it is of this form. So, the current rises during dt and falls during 1 minus dt, and this is delta I L, and let us say this is most of the time I naught. If it is a buck converter, and if it is a boost converter, it will be I in. So, let us say this is the average value. So, where is the maximum energy? When the current is maximum, you will see that the maximum energy is stored. So, this value is nothing but I average plus delta I L by 2 plus that, isn't it? So, I m is I average plus delta I L by 2, and you start here to calculate the energy. Now, all this is the calculation on the electrical side. Let us try to relate this to the physical parameters. Let us make a split. E is equal to half L I m square is half L I m into I m. Let us make a split. Let us take this from two different rules, that is, one is the flow based and another is the potential based. Now, if you take the Faraday's equation, where we know that V is equal to N d phi by dt, which is equal to L di by dt. As the current is linear, you can as well write it as N phi m is equal to L I m, because in the same time or given time, if the current has reached I m, the flux would have reached phi m, and N phi m can be written as N A C into B m. B m is the flux density, that is equal to L I m. So, this we can incorporate here. Now, let us come to the other aspect. What to do for this? Let us take another physical parameter. Notice here we are trying to relate to this physical parameter, that is core cross section area. Let us try to relate to this the other one, the window area. Now, let us see what the window area is. You see, we have this core. Let me take the simple EE core. Which is like this. Okay. So, this is a EE cores. You have two E joined together. And the former comes in here. The red line indicates the former. The red line indicates the former. So, this on the former is wound the windings. So, you will see the windings wound in this fashion. And you will see the other end of the winding also here. So, this is how it would appear. To picturize this better, let us go back again and have a look at the real inductor core. Now, if you look at this core, let me take out the bobbin. I will keep it aside. Then we have this core. Now, this is what I have been drawing just now. Two halves which are joined together, and you see here this is one opening and this is another opening, and the wire passes through, goes over and comes out through the bottom. And how is the former introduced? We take this former and you are introducing it like this. So, you see here this white portion is the former portion, and on the former is wound the copper wire. So, if I take a section cut, you would see exactly the figure that I have drawn there, of course, with many windings. Now, this winding has to fit into this area. We need, of course, to work this. Let me put this together. The entire winding will have to fit into this area, and that is called the window area. This is called the window area, because the other portion here, opening here, is nothing but carrying the other half of the turn. Therefore, in one complete turn, half of the turn is sitting in this opening and the other half is sitting in this opening. So, you consider only one opening as something available to you per turn. So, this window area is called AW. Coming back to the whiteboard. So, this window area is called AW. Now, within this AW window area, what should fit? All these n turns should fit. Now, each of these n turns have a cross section area. Now, let us say it has a cross section area A wire. Now, A wire is decided based on the thickness of the wire gauge, and the thickness of the wire gauge is decided based on the amount of current that a wire has to carry, and the amount of current, of course, is obtained from the electrical circuit side by electrical analysis. So, A wire is the thickness of is the cross section area of the wire. N of them should fit into this window area. So, n of them should fit into this area. So, AW should be greater than n into A wire. Now, let us do some simple math. AW should be greater than n into A wire. Normally, the amount of current that is passed in through the copper conductor is based on experience. So, let us say these are all current lines through. So, the current I which flows through now, there is this RMS component of the current which causes heat to be dissipated in the copper conductor. If the current is very dense, meaning for a given area, cross section area, the RMS current is very high, then the conductor can become very hot and lead to a lot of I square R losses. Therefore, there is appropriate amount of current density that has to be allowed. So, let us call J as the current density. It is usually expressed in terms of amps per meter square or amp per mm square. So, normally an amount of 3 amp per mm square, or 3 into 10 power 6 amp per meter square is the amount of current density that is considered as nominal. So, which means that when you say 3 amp per mm square, for every 1 mm square of this cross section area, 3 amps is allowed to flow through that cross section to keep the wire reasonably cool. However, you will find designers taking a conservative value 2 amp per mm square for very high powers to up to 5 amp per mm square for very low powers. This will lead to copper being cooler, this will lead to the copper being hotter. You will have more I square R losses with a higher current density. So, J, the current density, is I RMS by the area of cross section of the wire. Now, I RMS can also be written in terms of a crest factor. I RMS is nothing but Im peak value by crest factor by a wire. Just to put everything in terms of the peak value. Therefore, the wire cross section area can be calculated using this above equation, I RMS by J. Okay, now coming back to this issue of J and this, let us put it in this fashion. Im, that is, I am referring to this equation, equals J Kc a wire. Now, this is another interesting relation that we may use. Now, going back to this, we wanted this inequality to be satisfied. What is that inequality? It says AW window area should be greater than number of turns times a wire. And from the discussion just concluded, we could say N, a wire is nothing but I RMS by J, or it can be written as N Im by crest factor J. So, let us write Im as something that should be equal to AW Kc J by N. Now, here there is one more term that we need to add. keep this in the back of the mind. One more what you call a practical term. You saw that when you take the wire in the bobbin, when you start winding, you have the wires cross section which appear like this. I will consider just only the one portion, other portion is a duplicate, the other half of the winding. So, now let us say you put the layers of the copper winding in this fashion. There are many gaps here because the windings are circular cross section, and then you will see a lot of air gaps. And there is also the thickness of the bobbin itself, which is eating into the window area space. The thickness of the bobbin which eats into the window area space, the air gaps which eats into the window area space, and this wire itself. If you take this wire, if I blow this up, this cross section is having two parts. One is the outer sheath, which is the enamel, because the windings are sitting next to next. You don't need short circuits happening between the windings, and therefore, the wires are covered with a coating of enamel, which provides a natural insulation. So, therefore, the wire cross section, what we say as a wire, is pi r square, where this r is actually less than the total wire gauge radius because of this enamel which eats away some area. This is the thickness of enamel. Now, the air gaps, the bobbin itself, the enamel of the wires all eat up into the window area. Plus, there is also an additional issue, which is the skill of the winding. Now, that also eats up into the window area. Therefore, what is available is not AW, what is available is just KW AW, where KW is a factor which is less than 1. So, this factor is arrived at empirically. This is around 0.6 for inductors, properly wound inductors, and for transformers it could be anywhere from 0.2 to 0.4. It will be lesser, because when you talk of transformers, it is multiple windings. So, there will be a layer of insulation which also eats up into the same window area. So, what is actually available is KW AW. So, therefore, if I rewrite that, KW AW should be greater than N into a wire, which is the copper cross section, wire cross section. So, which is basically, if I use the inequality, N Im by crest factor j, or Im can be written as Kw, Kc, J, Aw by N. So, here we see that we are relating it with the other window, other area, the window area. Now, coming back to our energy equation, where half L I m into I m, which is half. Now, this was N A C B m into Kc, Kw, Aw and J by N. So, retaining these two physical parameters on one side, you will get Aw into Ac, which is called the area product, as 2 times energy value divided by Kc, Kw, J, Bm. And this is an important equation. Energy is obtained from the electrical circuit parameters. Bm is from the core material, which is, if it is a ferrite core, it is 0.3 as saturation, and the operating flux density may be around 0.25, J 3 amp per meter square, Kw of around 0.6, Kc is 1 in this case, and you can calculate the area product. Once you have the area product from the catalog of the core catalog, you run through the area product values and pick that area product value which is just more than what is calculated. Now, that would be the core that would be used for the inductance. So, at this point we know how to select the core for the inductance, and in the next class we will look at how we introduce air gaps if necessary, and choice of the wire gauges, and then see how we modify the design for a transformer too. Thank you.